All right. Good morning, everyone. I'm Jordan Rose. John will be joining me later. We both work at Apple on both the Clang and Swift compilers. And today we're going to be talking about embedding Clang for C interoperability, or how you can put Clang into your compiler to interact with C. So let's say you've invented a great new programming language. It has an amazing standard library, and you really want to get it out into the world. You want people to use it, but you can't do anything with it until you can talk to the rest of the system. Languages don't exist in a vacuum. So if you want to talk to the rest of the system, well, there's all these great libraries that are available, and you should be able to use them. But they're written in C. And most likely, C doesn't have the same ABI as your language. The way that your language does function calls and type layout and everything isn't going to be the same. And moreover, the API, the interfaces for those libraries are written in header files, which are written in C, and not your language. So what do we do here? Well, historically, the most common solution to this has been to write some kind of glue code. And that's usually written in C. It's some code that will talk to the runtime of your language and set up various entry points so that they can call into C and so that the stuff from C is returned back. And that's the approach you get with Java, with JNI, or with Python or Ruby extensions, or with a whole host of languages. In fact, this approach has worked pretty well, and so much so that there have even been projects that have been set up to generate that glue code for you. And so that's things like the Swig project. And of course, one last option that has been around for a long time is simply to extend C, and then you get something like C++ or Objective-C, where you have all of the C APIs automatically available. And the downside is you get all the bad parts of C too. But now there's a better solution. Just use Clang. Clang already knows how to talk to C, how to talk to C++, how to talk to Objective-C, and it already knows how to read those interfaces out of the header files on your system so that you can use all the libraries that are already there. So today, we're going to be talking about how you can embed Clang into your compiler so that you can use all of those existing APIs. We'll start off by me describing how we can bring in Clang as a library and then import various declarations from C. And then I'll hand it over to John, who's going to talk about ABI compatibility issues and how you can make your language compatible with C. And then finally, sharing an LLVM module between your compiler and Clang. We're also going to cover exactly what the Clang APIs provide and somewhat of what they don't provide, and some of the improvements that we might be able to make here in the future. Because this isn't a hypothetical case. Most of what we've done here is exactly what we've done in the Swift compiler to make it compatible with Apple's existing SDKs. Our goal for today is going to be able to call this function here or there. This is the flip over x-axis function. It's, completely normal geometry function. It takes a struct here that has two floats in it, and it's just going to alter the y-coordinate and return a new struct back by value. And we want to call this, in this case, from Swift, where we pass in an original point and we get a new point back. Now, there's a couple things here that do make this hard, though. First of all, we're declaring this static inline, which means there's no actual definition of this in some library. So we can't just call out to some existing code. Second, we're returning a struct. And more importantly, we're returning a struct of floats. And that's handled very differently on different platforms. So these are things that would normally make this a very hard function to bridge over into your language. But Clang can handle all that for you. So let's start with what it takes to get declarations from C and header files on disk into your language. So for this section, the first thing we're going to want to do is set up the Clang compiler instance that's inside your compiler. This is the central class that controls everything that Clang does and that manages any sort of action you want to do. Then we're going to talk about how to load Clang modules into your system. These are entities of API that are normally described in headers, and we want to bring those into the Clang translation unit. And finally, we'll look at the declarations that we actually care about from our language's source code and bring those into our language. So we'll start off with the Clang compiler instance. And setting this up isn't actually too bad. We start off with this method called create invocation from command line. And this is just a part of the Clang libraries that take a list of arguments, like you would provide on the command line, and parses them into a Clang compiler invocation. The Clang compiler invocation can then be used to construct this central class, the CompilerInstance. And this is the class, again, that we're going to use to do all of our actions within the Clang world. Once we have the CompilerInstance set up, we do want to customize it a bit so that we can map things back into the outer compiler for the language we're actually using. First of all, we want a diagnostic consumer. If there are any errors in the APIs that we try to import, we want to be able to show them to the user and not just dump them to standard error, or worse, ignore them altogether. The next thing that we might want is to track what modules are being imported, or other similar cases of just seeing what's going on in the Clang world to map back and take any actions we need in our compiler. And that usually goes through the preprocessor callbacks. Finally, once everything's set up, we would normally call a method called executeAction on the compiler instance. What does executeAction do? Well, first it sets up several important compiler components. These are things like the parser, preprocessor, the AST reader for loading modules, things like that. After we have everything set up, we're going to parse any input files, which in this case is just going to be a single file, probably just a memory buffer in memory that has a single declaration in it. This makes sure everything's been properly initialized and loaded. And then finally, what executeAction does is sort of finalize the AST, meaning it's going to say, OK, we're done loading in new declarations. Let's run any whole translation unit warnings. Let's clean up some of these objects that we've been hanging on to, anything like that. But we don't want to do that. And the reason why not is because we're using this not actually as a Clang compilation job, but as a way to get APIs from Clang into our language. So we don't finalize the AST so that we can keep loading new modules throughout the lifetime of our compilation. So to cover the things like, again, we're actually doing this, what works and what doesn't. Create invocation from command line actually works pretty well. There's a few steps it takes to get from this command line to an actual compiler instance. And it could probably be a little simpler for people trying to set this up on their own. But in the end, this API does what we need it to do, and it does give you the compiler instance that you need. Creating a custom diagnostic consumer is actually a little harder than it should be. In this cases, we end up duplicating some of the work from the text diagnostic printer in Clang. And that's not so wonderful. We don't want to duplicate work. But a little targeted refactoring here so that we can share some of the efforts that the text diagnostic printer makes would actually go a long way. The preprocessor callbacks, actually pretty good. They pretty much provide what you need. And executeAction, well, yes. So this part is unfortunate. And basically, the only reason we're doing it is because we always finalize the AST when we're doing it through Clang. So if we just change the interface here to allow not finalizing the AST, we could probably throw out this entire bullet point altogether and just use a single custom action. So we have our compiler instance set up. Now we want to load in our APIs. And we're going to do so using modules. What are modules? It's not anywhere in the C standard. So modules in Clang are self-contained units of API. They're a description of a set of header files that are known to work together and to not have any external dependencies beyond what is listed in those header files. The great thing about this is it means there's no cross-header pollution. A module only depends on the headers within the module and other modules that it explicitly pound includes or imports. You don't have to worry about macros from your program suddenly stomping on the meanings of various header files in the module. At a higher level, modules also are a sort of way to separate the semantics of declarations from the syntax of C. And they're doing so using the same technology as PCH. So when you load a module, what you're basically doing is taking the set of headers within that module and pre-compiling them. Clang will do this for you automatically in the background and pre-compile the module into a module cache. And just like PCH, this has the potential to dramatically speed up the compilation time of your program after the first build. If you want to know more about the motivation of modules and the implementation, then I really recommend you check out Doug's talk from 2 years ago. This is available on the LLVM website, llvm.org. So on our system now, let's say we have a library that's been modularized. It has its headers described by a module. And so we want to bring that module into our translation unit. We do this using the CompilerInstance method called loadModule. What loadModule does is going to bring the library in the form of Clang ASTs. And so here we see we have a type def, we have some functions. Everything's pretty much as you'd expect, as if you had just gotten it straight from headers. Once we've loaded the module, what we want to do is look for the declarations that were referenced in our language. And so in this case, that's the flip over x-axis function. Unfortunately, we can't do this. Clang doesn't actually provide an API to look up a particular name in a particular module. So the only thing we can do is do a translation unit-wide lookup and filter on the modules we care about. But if we do that, we do in fact find this function that we want to use. So again, how well does this work in practice? Well, load module is actually not a wonderful method. It gets the job done, but there's certain things that it doesn't handle so well. So it requires a source location, which is a little problematic if the cause of your import is not in a Clang source file. And it's a little awkward to use for submodules. If the submodule doesn't exist, it doesn't really help you know why, and it doesn't communicate that error very well to the user. Again, these are sort of small aesthetic things that a little targeted refactoring and improvement could really cause to be a great benefit to people trying to use this from outside of Clang. This next point, of course, is definitely something to improve, especially in any language that allows you to specify which module you're looking into. This isn't like C, but it does come up in Swift and several other languages that we know that do care about interacting with C. But there's still a bigger problem here, which is that Clang's model is to have a single translation unit with everything in it. What if two modules conflict? So consider these two hypothetical libraries, an older library that uses an unsigned integer as its status type, and a newer, completely distinct library that uses an enumeration. These two types can normally coexist in a program at runtime. There's no problem with that because types don't have symbols. They don't show up anywhere in your program. But if you try to load them into the same Clang translation unit, you get an error. At best, you'd get an ambiguity, and in the worst case, you actually have a conflict. Which status T do you mean? We recognize this problem in Swift, but we couldn't actually come up with a great solution right now. So it's something that we could look into improving in the future. All right, but we found our declaration. What is it going to take, then, to bring this declaration into Swift? Because we loaded this as a module, we actually don't need to be worrying about this textual form. Instead, we're going to be working with a Clang AST. And so we start with this Clang function decl. And I'm going to show you a simplified version of Clang's AST, the sort of object graph of declarations and types for parsed C functions and entities. In this case, we have a function, and its return type refers to a type def. And that type def has an underlying type, which is a struct. And that struct has two members, the x and y fields. And then, of course, the argument to this function is also this same type def. So this is a simplified form of the Clang AST. And what we basically want to do is we want to mirror this AST into Swift, into our language. And any time that you want to take a sort of object graph like this of the AST and preserve its structure, what you really want to do is walk over that and mirror things one by one. And the class to do that is called ASTVisitor. So here we're going to try to import the flip over x-axis function. And in order to do that, we need to import the return value. And in order to do that, we need to import the underlying type. And at that point, we probably want to import the fields. So now we have something that we can work with here. We have these two fields, x and y. And these can map directly over into our language. We have a var x with float type and a var y with float type. And now we can go back up to the struct and try to import that all together. Now, Swift in this particular doesn't have anonymous structs, but we are trying to mirror this directly over. So we'll try to do this as it is right now, and then we go back up to the type def, and we can mirror that over simply as a type alias. And then finally, we make it back to the function, and this function comes in as a function. Click. And so here you have it. After walking the Clang AST, we end up constructing a new AST from bottom up to build the Swift side of things. And on the Swift side of things, at every point, we're keeping a map back to the original Clang declaration. Why are we doing that? Because it's very important when you call a C function or use a C struct that you know how it was defined. And rather than try to mirror all of that information into Swift, we can just keep a link back to the original declaration and then let Clang do its job later on. But there is one thing that's a little funny about this. It really is weird in our language to have an anonymous struct like this. There's really no reason for it. In Swift, at least, when you declare a struct, the name is available at the top level, just like C++. So there's no need for this wrapping type def, which in Swift comes through as a needless type alias. So instead, what we actually do in our importer is something more like this. We have the struct show up on its own as a single node, still referring back to the original struct, but with the name from the type def. And this is an important note. When you're working in your language, you want the imported APIs to feel as natural as possible. And if that means writing special cases to handle things that are different from C, that's what you should do. So at this point, I'm going to say we're successful. We've imported a new function decal here that looks exactly like any other func decal from our language. It has a name. It's got arguments and the return type of this .2f type. And yet we still have this map back to the original Clang declaration. And we're going to need that when we try to go back from our language into C. And for that, I'd like to bring up John McCall.
I guess I'm on. So I want to talk to you about ABIs. ABI is a sort of overloaded word. Generally it means application binary interface, but that's obviously not actually meaningful. What I'm talking about as an ABI here is really, it's the contract, the sort of public contract about the implementation of a language. So every language on every single platform sort of forms a combination of an ABI. It's how that language is implemented on that platform. And it's necessary for all sorts of interoperation, just between different sort of compilers, different versions of the same compiler, also between compiled code and handwritten code, for example, in assembly, when languages support that, and between compiled code and various inspection and instrumentation tools that might exist on the platform, such as the debugger or dynamic analysis tools, or just simple, more obvious sort of things that are necessary for the implementation of your language, such as, for example, an unwinder and so on. The way that this is really going to surface up to somebody writing a custom front end for a language is that it's going to affect a couple of core things, such as how you lay out types and how you interact with calling conventions. So Clang supports a large variety of languages and language extensions, but almost all of those end up being defined at their core in terms of C. There's a couple caveats about this. Almost every single language extension that we support ends up requiring some sort of additional linker support that wouldn't have been necessary for C. And additionally, a lot of them require slightly different calling convention support and so on. But for the most part, the core of it is really defined in terms of the C ABI. So for example, the C++ ABI on Unix-like platforms follows what's called the Itanium rules, and all that really require it defines a couple of additional layout rules for C++ types, and then otherwise it's defined entirely in terms of the C ABI, except that it requires this notion of weak coalescing linkage in both the static linker and the dynamic linker. The Visual Studio C++ ABI is rather similar to that, but it also uses different calling conventions and has a special rule for passing C++ aggregates directly on the stack. Objective-C is very similar. The GNU Objective-C runtime is actually purely defined in terms of the C. Apple's own Objective-C runtimes require a lot more special linker magic. And then you have a lot of other things, just like the Objective-C blocks language extension, which are defined purely in terms of C. So that's other languages. What about the C ABI? ABIs for C are generally written by the architecture vendor and then sort of tweaked by the OS vendor. So the OS vendor is really the source of truth for this. So like Linux, for example, relatively recently changed their C ABI to change things like the stack alignment. The ABI covers a whole lot of things, most of which are handled automatically for us by the backend. That's things like the stack alignment rules, a lot of basic things like the object file structure, et cetera. And then a lot of things that are just sort of general system level rules like what types and so on are actually being provided. But a lot of the core of that is really just tweaked by the architecture's platform specific ABI. So having described that at a very high level, I want to make one important caveat about what an ABI really is. An ABI describes what the implementation does. That doesn't mean it actually changes how the language works. So for example, in C++, the Itanium ABI says that there's a vtable pointer at the beginning of any struct with virtual functions. You still can't actually read that in your source language, even though you know it's right there, because that's still undefined behavior in C++. So the fact that it is defined in some sense by the ABI does not act, and you know that you're compiling for a platform where it's done in this particular way, doesn't change the core rules of the source language that you're working within. So there's really two main bits of ABI that I want to talk about today. And the first one is layout of objects in memory. So oftentimes when you are importing some C API into your front end, into your language, you're going to want to embed C types into your own layout, into your own memory objects. So the basic rules for this are very straightforward. All you really need to know in order to embed something into your own memory layout is what C requires about its size and alignment. And you only really need to know about this if you're planning on exposing that pointer to C. If you aren't planning on exposing a pointer directly to C in any way, it doesn't really matter how you store it. You could, break it up into many small pieces. You can use compact away padding and so on and so forth. But if you're going to expose it to C, these are the rules that you need to know about. Every complete type in C has a size and an alignment. The size is always going to be a multiple of the alignment, except in some special cases about type defs. Usually that size is going to include some special storage. So there's an ABI rule here about, well, what do you get to assume about that storage? And the answer is basically nothing. So if you are ever storing to any sort of sub-object of a C structure, basically the language says that all of the padding in that entire structure is invalidated. And this is actually something that very frequently happens. So just because things will, the compiler reserves the right to do mem copies, reserves the right to do larger stores than is necessary when that becomes a more efficient way of doing the store. So for example, in this very simple structure type where I've got 3 different things, I've got both tail padding after a long double because the size of the long double was actually rounded up to its alignment. And then I've got additional tail padding after the trailing char to bring the entire structure up to its alignment. So again, this is only something that you really need to know about if you are going to directly share pointers to your internal storage with C. But typically, that's actually going to be a very important thing to do. So it's often tempting to do your own structure layout when you're writing your own front end. You're like, OK, well, I know all of these fields. I know what their fundamental types are, et cetera, et cetera. I'm just going to, a lot of really common cases just sort of naturally fall out, like that point2f example that we mentioned before. Obviously, I can just make an LLVM struct type that has 2 float fields in it, and everything is going to be great. So for example, in this, in that struct that I just brought up, it just works. Like assuming I've got the LLVM data layout right, I can just make a pointer and a long double type and a char, and LLVM will give this thing will do all the right layout for me automatically. So don't do this. It's a mistake. It's very, very tempting. I understand. I've done it so many times. It's almost always a mistake. So the problem is that there are some very high-level guarantees that C and C++ give that do make the layout seem very, very obvious. And ends up being that platform ABIs tend to use almost exactly, because of those rules, platform ABIs are almost forced to use exactly this one extremely common algorithm for laying out struct types. It's almost completely universal. It's not technically guaranteed, but anything that didn't follow it would literally just be wantonly wasting space in structures. But there are a lot of exceptions to it that aren't really covered by that. So for example, that rule doesn't really specify what you do for bit fields. And it turns out that what you do for bit fields is massively different on all sorts of different platforms. And then actual C is very little like standardized C. You have a lot of attributes, you have a lot of pragmas, a lot of which can affect basic layout. And all of that is something that you do not want to get into the business of carefully repeating yourself. And then there's another story of what you're going to do if you actually have a C++ structure around. So don't get into this. Don't fall into this trap. You can use C. You can use Clang to just lay out the type. So again, the AST context can tell you the exact size and alignment of the type as C lays it out. There's an AST record layout that will give you the offsets of all the individual fields. Irogen provides interfaces that'll help you lower that type to an LLVM IR type, and then do common operations like projecting out the address of a field and doing loads and stores to bit fields. The other major ABI issue I want to talk about is calls. The main sort of way that this takes effect here is turning a Clang function type into an LLVM function type. So our inputs to this algorithm are going to be a sort of AST level calling convention, and then the formal parameter types and return types. And the outputs are going to be an LLVM calling convention, parameter types, return types, and a whole bunch of parameter attributes. A question that we get very, very often is, why does LLVM not just really use something that's much more natural to lower? Why do LLVM IR types feel so completely different from Clang types? So the problem is that it's very easy to get to a state that feels approximately right. But there's so many things, so many subtle things in processor-specific ABIs that end up affecting calling convention in very significant ways. So the exact structure of a union, which union member comes first, et cetera, that sort of thing often affects how a union is passed. The existence and placement of bit fields within the structure, all sorts of attributes that can be layered onto unions and structs. Oftentimes you will have two types which feel like they ought to lower down to basically the same thing in terms of primitive representation, but in fact the ABI calls out one of them as being a special case. The really standard example of that is a structure with two floats like point2f and a complex float. Complex floats are often called out by the ABI as having special rules for how they're passed, whereas a structure may be passed in memory just as there not being a special case for it. So if we wanted to actually go down the route of saying, look, we're going to have the LLVM IR type system be extremely natural and always be able to match it in a very clean way, what we would have to do is basically reflect the entire Clang type system into LLVM IR. And that's really just not a workable solution. So what we end up with instead is this sort of mutual aggression pact between the front ends and the back ends, where the back end figures out a whole bunch of kind of hacky rules about like, okay, how are you supposed to request this specific type of argument to be lowered in this passed in a specific way, like on the stack, in a very specific register, and so on. And then the front end massively contorts the argument list and the LLVM IR types in order to sort of match that as best as it can. So nobody's going to pretend that this is the cleanest thing in the world, but let's go back to this flip over x-axis example. On ARM64 for Apple, this is the LIR type look for this looks very clean. On i386, this is more or less the same, except that instead of returning as a structure, we return as a single i64, which requests a very specific way of returning it. On ARM v7, it gets really different because all of a sudden we need to do an indirect return. And for some reason, instead of passing as two floats, we need to pass as this array thing. And then it all really just goes completely crazy, as things often do, on x86-64, where the ABI is actually telling us that we should pass these things in a single and return these things in a single vector register, which means we use vector types on both of these things. So again, this is really something that you do not want to have to duplicate yourself. There are some cases where you wouldn't necessarily have to go through Clang, and that's really handy for when you're writing code that might have to interact with your language's runtime. So when you just have an LLVM type that feels like it would naturally turn into a bunch of things that are basically pointers or pointer-sized integers, on standard CPU architectures, the naive lowering of that will actually work. So that's more or less an informal guarantee that you can rely on cross-platform for IR. But there's a lot of that guarantee is extremely limited. Don't try to stretch too far. You should really get into the practice of like when you're interacting with a C declaration and you don't know almost a lot of details about it, you really need to be using Clang in order to lower the interaction. I don't think anybody wants to claim that this is the cleanest solution or a beautiful solution, but it's what we're stuck with right now, and you really don't want to be in the situation of repeating all this logic yourself. What I would suggest if we want to fix this is that we should really move in a direction of actually going the other way and find ways to have very straightforward, consistent rules about how specific types are passed by default, and then have ways for the front end to actually directly customize and specifically say, please pass this particular thing in this particular register, and so on. So basically moving more of the task of calling convention lowering into the front end. So again, the solution here, you really should be using Clang. I'm going to talk very, very briefly about the problems of sharing a module with Clang. Clang's IR generation is really set up to be actually very flexible and forgiving. So for the most part, Clang is going to basically assume that declarations and all sorts of global declarations might be screwed with behind the scenes. That's actually really convenient when you're writing your front end, which is basically going to screw with Clang's declarations behind the scenes. So it doesn't matter that IR types aren't necessarily going to match up. Clang really goes out of its way to make sure that really just works. So if Clang has to emit a definition of something, it might have to change the type. That is something that you have to be aware of when you are asking Clang to emit definitions. Another thing that you might need to be aware of when you're asking Clang to emit definitions, like that static inline flip over x-axis function, is how Clang does lazy declaration emission. And again, there's a very straightforward set of rules that you have to sort of follow. This is something that we're looking to really improve on in future releases of Clang. It's something that I really invite a lot of people to help with this, because it's a problem that can really benefit from more eyes and more use cases. So to summarize, you can use Clang to import types and declarations directly from C so that you can access them in an extremely natural way in your language. But you should really use Clang, take advantage of the existence of Clang in order to do work for you, instead of trying to just keep on hacking on more and more new special cases into code that just kind of seems to work. Please just use the facilities that we already provide, and things will work out much better for you in the long run. Thanks.
We have a few moments for questions. Any questions?
Now, this is sort of a practical question. It sounds like actually embedding Clang is a little bit more complicated right now than we'd like it to be. Do you have any plans to put together a short tutorial on how to, let's say, as with the debug info, take Kaleidoscope or something like that and say, here's how you make FFI calls to C by embedding Clang in this tutorial? Because I think that would be pretty helpful for everybody else who wants to do it.
That'd be super cool. My manager's sitting in the front row, so I don't know exactly when we get time to do that.
Any other questions?
Yeah, so we're basically doing the same thing in Julia, and I'd like to echo the source location thing that you touched on briefly, because it's actually really hard to know whether you have to pass a valid source location, and whether your source location needs to be in the scope chain, and ideally I'd like to actually annotate my Julia source that then translates down to C with an actual Clang source location. So if it's invalid C, then Clang would tell me in my Julia code, but some functions complain about that since it's not a C source file. So I think it would be nice to clean up the whole handling of source locations in Clang. So either with documentation that tell me, oh, this always needs to be valid and always needs to be in a source code, or maybe this is only used for diagnostics.
Definitely I'll come talk to you afterwards. If you want to hear us complain about source locations, you can track either of us down after the talk.
Okay, I think someone had their hand up over here. No? Any other questions?
At the beginning of the talk, you alluded to the question of sharing LLVM during embedding. Do you have a quick summary on that, on the issues? Sharing an LLVM instance?
Yeah, I was a little bit short on time. So most of the issues I kind of ran down, The issues that you're going to run into whenever you have two different IR generators emitting into the same module are going to be mostly about, well, the points of interaction between those two things are always going to be global metadata. In particular, if there's any global metadata that has to be set, and that is sort of special case by the backend, you have to decide which one is going to emit that. Otherwise, it's all about like global declarations and global definitions, and for the most part, that just falls out as long as both sides agree about what the type should actually be. So if you use Clang to emit a declaration for you, and then that's fine, and you don't need to do any additional worries. If you want to emit your own declaration for something, for example, if you have Clang code that is actually referencing a declaration that's actually going to be defined by your code, the big limitation here is that the definition of something really has to have a very specific type, right? So whichever front end is emitting the definition of it, if there is a front end that emits that definition, kind of owns the type that it is. And any other front end really needs to make sure that it's always holding onto that with an asserting value handle that will then be, that can be turned from a global variable or function reference into something that's just a bitcast of that to the appropriate type. So Clang is very good about always doing that itself, basically because there are so many crazy C extensions that it has to be paranoid about. In particular, like you can take, either with extern C or with the ASM label attributes and things like that, you can basically take an arbitrary entity and give it an arbitrary LLVM label, which basically massively screws up any sort of hope that Clang's backend could actually, that Clang IR generation could actually have any sort of real invariance about what global function or variable is actually there. So Clang is generally very good at being paranoid about that. So that interops very well with other front ends. Other people's front ends are not necessarily as paranoid about that because they probably, if you're smart, you've probably done this in a way that doesn't have quite as many brutal things that just completely screw up any sort of hope for having invariance in your own code.
Okay, let's thank the speakers one more time.